Hello everyone, welcome back to the second session. In the first session we saw that what are near duplicate videos, what are the problems of near duplicate videos, possible solution to overcome the problem of near duplicate videos using the perceptual hashing technique. Right. So then we will see that in this session what is perceptual hashing technique. Okay. Now a perceptual hashing technique is a function that takes two inputs, a video and a secret key k, to produce a k-bit binary hash. So what I mean to say was, say suppose I consider that this is a black box hashing function. It takes two inputs. Okay, one is a video and then the other one is the key, secret key k. Okay, to produce a hash, perceptual hash based on the perceptual content. Now you may ask, why is this secret key? Secret key is included to improve the security. Okay, I hope you've understood that perceptual hashing is just a mapping function. What does it map? It maps the video onto a digital bits with the help of the secret key. Okay, fine. Okay. Now, what are the properties of the hash that we extract? What are the desirable properties? It should be a one-way function. That is, I should not be able to get back the video from the hash. Okay, obviously, right? Because, the second thing is it should be compact. That is, size of the hash must be much smaller than the size of the video itself. The next point is it should be perceptually robust. What do you mean by that? Now, say suppose, let me consider a video, say video 1. Let me consider another video, say video 2. Video 2 is perceptually similar to video 1, or video 2 is a near duplicate of video 1. Now, I'll extract the perceptual hash from video 1 and video 2 and say I'll represent it as h subscript v and h subscript similar. Now if I measure the normalized Hamming distance between these hashes, then it should be close to 0. On an average, you take any number of near duplicate videos. When you measure the normalized Hamming distance among the hashes of the video and its near duplicates, it should be close to 0. Okay. Next is the visual fragility. Suppose say I have video 1. Now say let me consider another video 3, V3. V3 and V1 are perceptually different. That is, they are completely different videos. It is looking different to the human eye. It conveys a different meaning. And say suppose I have generated the perceptual hash for each of these videos. Okay. Now the normalized Hamming distance on an average for such different videos should be very close to 0.5. Okay. Next, here in the perceptual robustness, please remember that when you are generating the perceptual hash for a similarly looking videos, it's assumed that the secret keys are same. Even in the visual fragility, even if the secret keys are same, doesn't matter, since the videos are different. Its normalized Hamming distance should be very close to 0.5. Okay, and what about the unpredictability? Now suppose I have a video 1 and video 2. Video 2 is a near duplicate of video 1. Now this time what I'll do is I will generate a perceptual hash from video 1 using say secret key k1. I will generate a perceptual hash from video 2 using a secret key k2. So please concentrate that I am using two different keys to generate the hash for near duplicates, because v1 is original, v2 is a near duplicate of v2. We have told already, right? So I'm trying to do that. And again, in this case, if I try to measure the normalized Hamming distance between these two videos, it should be close to 0.5. Okay, so these are the desirable properties of perceptual hash. Okay, since we are generating from a video, it's called as perceptual video hash. Okay, so a hash or a digital signature extracted from the video based on the perceptual contents. What are the possible applications of perceptual video hashing? The content-based authentication, copy detection, content-based identification. Okay, next. Okay. Let us now see or review the existing methodologies in the literature. One is there are so many algorithms. We have just hand-picked a few which are very popular or which perform well. Okay. First one is two-dimensional radial projection based video hashing by Ruvar et al. Ruvar et al. Proposed to generate a perceptual hash based on the radial projection of the luminance values of the pixels of an image, and then extended the idea to the keyframes of the videos to form the radial variance vector. Let me elaborate. You have an image, they radially projected the pixels of an image, okay, and then they called it as a radial variance vector because they are trying to measure the variance along the radial projection, and hence they have called it as a radial variance vector. And then they have done it for the entire pixels, okay, of an image, and then after they have obtained a radial variance vector, they have projected onto the DCT basis. Why? Because we need to get a compact hash, right? So they have projected onto a DCT basis. Only low frequency DCT coefficients are selected and quantized to obtain the rash vector, that is a radial hash vector. Why? Because most of the meaningful information would be present in low to mid frequency, and hence they have selected only those DCT coefficients they have and quantized it to generate the rash vector. What is the drawback of this algorithm? It is exposed to all the non-keyframe based attacks such as frame dropping, malicious attacks on non-keyframes, and unwanted frame insertions. Please remember that they had proposed the method to the image and then they had extended it to the video, and in that video they have only applied on keyframes and not on all the frames of the videos. Okay, so that is why it is exposed to all the non-keyframe based attacks. Let us go to the next algorithm. The next algorithm is a three-dimensional discrete cosine transform based video hashing by Koskun and Sankur. Koskun and Sankur proposed a video hashing technique based on the three-dimensional subspace projection of the luminance components of a video onto a DCT basis. So they treated the entire video as one single entity. They applied three-dimensional transformation, three-dimensional discrete cosine transformation on the luminance components of the video. Now, once you have the transform domain coefficients, they selected the low to mid frequency coefficients, quantized it, and generated the hash vector for a video. Okay, what is the drawback? It lacks in security because the basis functions is predefined, that is, it is deterministic. To improve the security, the authors generate the video hash using randomized 3D basis functions. The video hash based on this 3D randomized basis showed inferior performance compared to that of the deterministic basis. Okay. Next algorithm, video fingerprinting based on centroids of gradient orientations. This algorithm was proposed by Sunil and Yo. They obtained the hash values based on the centroid of gradient orientations. The centroid of gradient orientation values give the direction, that is the angle information from the difference of adjacent pixel values. Each frame of the normalized video was divided into blocks, and then for each block the CGOs were calculated. Final hash of the video was obtained by concatenating the CGOs of all the blocks. What is the drawback? The algorithm is weak under geometric distortions like the rotation attack. And also, as the number of frame increases, the length of the hash also increases. Next algorithm, tensor decomposition based video hashing by Lee and Monga. They modeled videos as third order tensors. The authors experimentally validate that this type of video modeling captures its spatial and temporal essence. The multilinear subspace projection of tensors, such as low rank tensor approximations via parallel factor analysis, are used for generation of perceptual hash from the videos. Each third order tensor is factorized into outer product of three vectors. These vectors are used to form the perceptual hash. Basically, this is a multilinear subspace projection techniques. The video is treated as a third order tensor. A tensor is nothing but a multi-dimensional array. For example, the matrix is a tensor of order 2, a cube is a tensor of order 3. So that's it. Okay. The performance of this algorithm was found to be robust to most of the content preserving distortion except for the malicious modifications. Further, there is a scope for the generalization of tensor decomposition to improve the performance of the algorithm. Okay. Now, what are the challenges in extracting the perceptual hash from the video? One is the content authentication problem. Why? Because the incidental distortions such as compression, noise addition, and filtering are unlikely to change the perceptual content, and the video can be considered still authentic because they do not change the meaning, right? And these are all the operations that a video would undergo for any system, right? In any communication system. So it should still be considered authentic. The performance of the existing video hashing algorithms for these tasks has scope for improvement. The other one is near duplicate identification problem. Now see, the compression, yes, and then the original, yes, because it's required, it's a part of a process. Now, but here, near duplicate identification problem because unauthorized multiple creation of popular videos in different file formats, spatial size, and frame rates. And we have already discussed that because of the improvement in the technology and easy availability of tools, now it's become an easy tool, okay, to modify and then again upload it. So the number of near duplicates have increased enormously that we have already discussed, and it causes a huge burden. Now we have to now distinguish between, yes, which is part of that, and then which is part of the process like compression and all, and which is that unauthorizedly done and then trying to burden the server. So these are the two challenges that needs to be addressed when you are trying to extract the perceptual hash and then trying to implement an application for a given application. Okay. Now let me discuss what are the algorithms that we proposed. Out of many algorithms that we proposed, I would like to discuss only the two algorithms. One is the random projection. In that we have two variations. We will see that. And then one is the other one is on Tucker decomposition, which is also a multilinear subspace projection technique. Okay, first let me introduce you to the random projection technique. Now, before going to the random projection technique, I want to tell you about the lemma, the Johnson-Lindenstrass lemma. What is that lemma? Let me state it as it is. A set of n points in d-dimensional Euclidean space can be mapped into random k-dimensional Euclidean space without distorting the distances between any pair of points by more than a factor of 1 plus or minus epsilon. Okay, now say suppose d there are n points in high dimensional space. Okay, everyone wants to reduce the dimensionality, right? So now we are using random projection technique to reduce the dimension, and k is the lower dimensional space, d is the higher dimensional space, k is the lower dimensional space. Now these n points were in high dimensional space. We have applied random projection techniques and we have got, say, the points, n points in k dimensional space. Now according to this lemma, it doesn't distort the distances between any pair of points by more than a factor of 1 plus or minus epsilon. K is in the order of epsilon to the power minus 2 natural log of n. Okay, where k is very much smaller than d, and epsilon lies in the range of 0 and 1. And the second condition is that, say suppose u and v are the vectors in the high dimensional space, and f of u and f of v are the vectors in the low dimensional space. Here we have tried to measure the Euclidean distance between the vectors in the high dimensional space, which is represented as L2 norm square between the u and v, and here also it is the same thing. This and this and this both are same. Now f of u and f of v. Okay, now we have got the points in the low dimensional space. Again, here we are trying to measure the Euclidean distance between the points in the low dimensional space. Now, as per this lemma, the distances among the points in the low dimensional space is bounded by, the upper bound is 1 plus epsilon, the lower bound is 1 minus epsilon times the distance between the points in the high dimensional space. To explain you with an example, let me take a simple example. Okay, now suppose I have 2 points u and v, vector u and vector v, in 3-dimensional space x, y and z. Okay, now this point we are trying to measure the distance, say, which is represented here. Now say suppose these are the points in d dimensional, that is points in higher dimensional space. Now we have used a random projection technique and dropped this points or mapped this high dimension points in high dimensional space to low dimensional space. Now say let me consider only 2-dimensional, that is x and y axis. Now I have reduced it, which is represented as f of u and f of v. Now I try to measure the distance between that, which is represented as L2 norm square between f of u and f of v. Now this distance compared to this distance is bounded by 1 plus or minus epsilon, right? That's what is the JL lemma trying to tell you. Okay. Now we have used the Achlioptas random matrix, the random projection matrix that satisfies the JL lemma. The Achlioptas random matrix is very simple because it has got +1 and -1 with equal probability. So if you take a random projection matrix of dimensions k by d, then there are equal number of +1 and equal number of -1. Now just see, let me explain you the concept of random projections using Achlioptas random matrix, and this, it's proved that this satisfies JL lemma. When I say it satisfies JL lemma, when you are trying to reduce, say this is a vector in high dimensional space in RD, I'm using a transformation matrix or projection matrix. So I have got this vector in lower dimensional space. Remember, P1, P2, PD, this is a point in high dimensional space. This dimension is k by d. So k by d and d by 1. What is the resultant order? K by 1. So this vector is of the order k by 1. So this is a point in the low dimensional space. Now since this Achlioptas random matrix satisfies JL lemma, we are sure that when we do on multiple points, the distances are preserved. So it's a distance preserving transformations and random projections. Now the other advantage of here you can see that it in other advantages of Achlioptas random matrix is that it includes only +1 and -1. And when I multiply these two, you may be thinking it's multiplication, right? But it boils down to only addition and subtraction, because I'm just performing addition and subtraction, so there is no multiplication involved. So it reduces the computational complexity when I'm trying to reduce the dimensionality, that is mapping a point in a high dimensional space to a low dimensional space. Okay. Now let us see that how the random projection technique is used to extract the perceptual video hash from a video. Okay, so now I have a video I apply, I'll explain elaborately. We'll apply some standardization that includes pre-processing and normalization, randomize it, then apply random rejection technique using the Achlioptas random matrix, and then finally compute the hash, and then we have got a digital signature or a perceptual hash or a video fingerprint. All these terms are interchangeably used in the literature based on the perceptual content. That's the main thing. Okay, so let us go in detail. Okay, now what are the input to the perceptual hashing function? One is the video input, the algorithm parameter, x, y, z. The x, y, z represents to what size any given video should be brought down to. U, V, W represents the subcubes. Okay, and n represents the number of subcubes that you need to take. K represents the length of the hash, what should be the length of the bits that you extract from a given video, and epsilon relates to the parameter that we discussed now in JLMA. Okay, so pre-processing norm. So we convert the input video, which is generally in RGB format, into a sequence of gray level frames. We represent it as V gray. We normalize V gray via temporal subsampling and spatial resizing to obtain V of size x by y by z. So whatever could be the dimensions of the video, it could be the spatial dimensions or temporal dimensions. Temporal dimension in the sense the number of frames, whatever it could be, we are normalizing it and bringing down to x by y by z. Suppose the input video is of say it's a high definition. Now I am modifying it and say bring it to 128 by 128 by 128. Suppose I have a high definition video of 3 minutes duration, and then it has got say 1000 number of frames. I'm just taking randomly 1000 number of frames. Then it is brought down to 128 by 128 by 128. So 128 say rows, 128 columns, and 128 in temporal direction. So 128 frames. So whatever it could be the video, we are normalizing it and bringing it to this particular size. So now you can see that 128 by 128 by 128 can be thought of as a cube. Okay. Now we'll, depending on a secret key k, we randomly select n overlapping 3D subblocks or subcubes. So I have a bigger subcube, and in that I am trying to take a smaller subcubes, and then we will try to apply the random projection technique on the subcubes and not on the entire cube. Okay, why? Because depending on a secret, we randomly select, we take overlapping subcubes, because to improve the security, we want a secured hash. But when it comes to near duplicate video retrieval, may not be required. The secret key may not be required. Okay. So Vi, so n subblocks, each of size U, V, W. Remember, U, V, W is much smaller than X, Y, Z. So U is less than X, V is less than Y, and W is less than Z. Okay, now we have got each subcubes. So we have got say subcubes. Now this subcubes is then drawn as a line. So we are making it as a single column vector. Okay, so concatenate in the column of each subblocks to form a vector. Now please remember, now it's a subblock. So suppose the subblock size is say 32 cross 32 cross 32. So it is still of high dimension when I vectorize it. So it is 2 power 15 the dimensions. So it's still a very high dimension. Now it's a column vector. Now I have taken n subcubes, right? So from each subcubes I have got one vector, one high dimensional vector. So I have n high dimensional vector. Now these n vectors can be treated as points, n points in high dimensional space. So we are will try to apply the random projection technique on this n high dimensional n points in high dimensional space. Okay, so we concatenate and form it as a feature matrix where f1, f2, fn are all vectors of dimension d cross n, where d represents u cross v cross w, n represents n vectors obtained from n subcubes. Okay, so this matrix is of dimension d cross n. So applying random projection is nothing but just multiplication, right? We said right? So now the hash matrix is obtained by random Achlioptas random matrix multiplied by f, the feature matrix, 1 by root k. This is just a scaling factor. Okay. Now, please remember the f represents all the points, n-dimensional endpoints in high-dimensional space. I am multiplying it. Now I have got n points in the left-hand side. The h will have n points in low-dimensional space. The dimension of each of this vector is of d, and then the dimension of each of this vector is k, where k represents the low-dimensional space. Okay. Length of the key basically. Now generate the intermediate hash vector, because now we want to generate a single vector, right? Now I have got multiple this thing, right? So for n I have got like this vectors, high dimensional, and then these are the vectors, right? So vectors we have got, so in lower dimensional space. But I want a single vector, so what I would do, I have applied the addition of all these things along the row wise, and then we have got a single vector. That is what is this operation. Okay. Once you have got a single vector, we have to I have applied median based quantization. So perform median operation. So rank order it and then select the median value. Since it is a even number, because we had said that k will be even, we will take the average of the middle numbers. That's the median value. Depending on if the values are less than the median, then it is made 0. If the value is greater than median, then it is made as 1. So like this, we generate a hash vector from the video using the random projection technique. Okay. So this was the database that we had used from TrekVid, OpenVideo, Refit, and XIPH. A number of videos was 1000. A minimum spatial resolution was 192 by 144. Maximum spatial resolution was 640 by 480. A minimum number of frames was 66. Maximum number of frames was 11,415 for a given video, and video format was in MP4. Okay. What was the spatial attacks considered? Addition of white Gaussian noise, Gaussian blurring, average blurring, brightness modifications, contrast modifications, cropping from the borders, rotation, adding the watermark. So in spite of this, it should say that yes, these are near duplicate videos. Temporal attacks, regular frame dropping and interpolation. Spatio-temporal attacks, compression, unwanted frame insertions, and then the reverse play. So unwanted frame insertion would result in malicious modification, and then here the watermark can also be considered as the malicious attack. Right. So we are considering these are the attacks. We have categorized into spatial attacks, temporal attacks, and spatio-temporal attacks. Okay. Now before that, we have to check whether the hash that we have extracted from a given video satisfies the desirable property of perceptual video hashing. One is it should be compact. Yes, it is just compact. It is invertible, so we cannot get back the video from the hash, from the bits, correct? But there are the other things that we said was the unpredictability, visual fragility, and the perceptual robustness. These properties that I am talking about, the desirable properties of the perceptual robustness, visual fragility, and unpredictability. So let us see how do we experiment that and validate whether it satisfies. Okay. Okay. Now unpredictability. What is the unpredictability? Now say suppose I have a video. Now I'll choose a video and I'll use 1000 different keys to generate the perceptual hash from the same video. Okay. Now obviously video is same, but since this keys are different, what is the expectation? The hash should be different, and the normalized Hamming distance when I measure, it should be very close to 0.5. Okay, so this was done for a video using 1000 different keys, and then the process was repeated for 224 videos, and then it was plotted. Now you can see that the normalized Hamming distance is concentrated around 0.5. It is ranging between 0.3 to 0.7, very closely, approximately. Okay, so it is satisfying that property. Now what about the visual fragility property? Now say suppose I have 224 different videos. Using the same secret key, I generate the hash. Of course, because they are different videos, when I measure the normalized Hamming distance between these videos, it should be very close to 0.5. Now I repeat the same process for 999 keys. In total 1000 different keys, and now you can see that again the normalized Hamming distance on an average is close to 0.5, ranging from 0.2 to 0.8 approximately. Now what about the perceptual robustness? Now I have an original video and its near duplicate video, or content or have applied some content preserving operation on a video and obtained its perceptually similar video. Now when I measure the hash normalized Hamming distance between the hashes of that, assuming that I have used the same secret key, its normalized Hamming distance value should be close to 0. Now you can see that it is shifted towards 0. Now it has got a mean value of around 0.25, ranging from 0 to 0.5. Yes, so here also it is satisfying the perceptual robustness property. Now if you see that, so for the different videos it should say different. So how do we check that? Its normalized Hamming distance value should be around 0.5. If it is perceptually similar video, its normalized Hamming distance should be around 0. This is what it is. Now if I superimpose these two things, I'll get this. Now here we can see that, okay, the one in the red indicates that there are different videos. The one in the blue indicates visually similar videos or perceptually similar videos. So suppose I put a threshold of 0.35. So if I normalize Hamming distance above 0.35, then I'll say that it is different. If it is below 0.35, it is same. Now you can see that there are still misclassification, because there are some visually similar videos whose normalized Hamming distance is greater than 0.35. Also you can see that there are some two different videos, perceptually different videos, at their normalized Hamming distance is around 0.2, 0.3, and hence there are some misclassifications. Okay, so we always try to minimize this misclassification. Okay, so this was about the extraction of a perceptual hash from a given video using the random projection technique. To be very specific, the Achlioptas random matrix is acting as a random projection matrix. Here it is computationally simple. Performance is satisfactory, but definitely has a scope for improvement. So what we can think is that instead of applying dimensionality reduction directly on the luminance values of the video, we can select relevant features from the video and then apply the random projection technique. And indeed, that is what is the topic of the discussion in the next session. Thank you so much for attending the session 2. See you soon in the session 3. Thank you.